The third topic for this week is numerical methods. So numerical methods are a branch of mathematics which was designed to help solve complicated or outright impossible to solve equations. Since they are approximations, they are technically incorrect. However, most of the time in complicated systems, they are the only way that we can get useful information from the system. With the advent of faster computers, high-power computing, supercomputers, that sort of thing, they have become very useful tools for engineers where we can take complicated systems and get the information that we need out of them. So one of the things we can use this for is a field called Computational Fluid Dynamics. So we're looking here at a car where we're doing some aerodynamic testing of it. The equations that define fluid flow are very complicated equations, and except for very simple systems, we don't have solutions for them. However, if we take a numerical version of them, we can get information that we normally wouldn't be able to find out. So when we're looking at this car, we'll notice that there's a lot of turbulence towards the back and within certain areas. We might be able to change the design of the car so that we can minimize the turbulence and we can get a better solution. We can also look at the stress and strains that are on parts in machines that we manufacture. So at the moment we're looking at a piece from an internal combustion engine. Now, inside of an internal combustion engine, there's usually very high forces at very high frequencies. What this means is that any failure that happens can quite likely be very destructive to the engine. So we need to design the parts so that we know that they're not going to break. In what's called finite element analysis, we can take a part, apply forces to it, and determine where the highest pressures on the object are going to be and the highest strain areas. So that if we find out that this area is going to break under normal loading, we can change our design before we even make it, which can save quite a lot of money and time. So another application which isn't engineering related as such is in video games. So now that gaming platforms are becoming much more powerful, we can introduce different effects to our games to give a more realistic feel. So the screenshots that we have here are from the recently released Battlefield 3, which allows us to have destructible environments. So these destructible environments are very complicated systems where we have to be able to track all the different particles and pieces of buildings that we destroy. And although this is an engineering application, it's very heavily towards numerical methods. So let's look at what makes up a numerical method in a system that we can all understand. So I'm going to explain to you the background behind what I call a bouncy ball simulator. Say we have a room that's filled with many bouncy balls. Now, each of these bouncy balls will have several things that we need to know about them so we can describe the room completely. Those things are position, which we will give in x and y coordinates, for example. Velocity, so each particle is going to have its own velocity. And finally, every ball is going to have certain forces acting on it which change with respect to time. So how we relate all these together is by using Newton's second law, which says that the sum of the forces acting on a body is equal to mass times the acceleration of the body. So I said before that our force will be constantly changing, and this is going to be our main concern with this problem. So some of the forces that will have acting on these balls will include weight. So each ball will have its own weight force acting in the direction of gravity. And that force is given by mg. We can also have a drag force acting on each of these balls. So when we're moving through a fluid, there will be some drag associated with that. We will also have forces associated with the collisions of these bouncy balls. We might also have gravity acting between each of these bouncy balls. So usually when we look at that, we think on the scale of Earth and the Sun, where the Sun is pulling the Earth slightly towards it. In the same way, any two of these bouncy balls might have some gravity acting between them. With collisions themselves, there might be some friction occurring. So when these balls collide, they'll rub against each other slightly and generate a bit of heat. Also with collisions, we might have some cohesion. So these balls might be slightly sticky towards each other, and that would generate another force. And similarly, there could be some adhesion, which is the same as cohesion, except it's between a ball and the wall. Also, the balls might become slightly deformed, so that any of the forces acting on them might not be in perfectly spherical senses anymore. Also, there could be some other forces associated with this system, which I haven't included here. So now if we look at these forces, we might be able to say, well, some of them don't really contribute to much, and we can just ignore them. So the first force that we can rule out is the gravity acting between two bouncy balls. So in cases where these bouncy balls are quite small, so that they can fit in our hand per se, the gravity will be negligible. Weight force we will definitely need. We might be able to say that drag force is going to be quite small because they're not going to be moving fast. Collisions will definitely happen, and within collisions, friction is very important. We might be able to say that the balls aren't sticky at all, so there will be no cohesion or adhesion. There will be no deformation of these balls, and there's no other forces. So this is how we firstly approximate our system so that only the important parts, well, only the most important parts are going to have an effect. So how we would start solving for this is that at our initial point for each of the particles, we would calculate what the forces acting on them are. So that's the weight, and we will check if there's any collisions between particles. And if there are collisions, if there's any friction acting on them. So once we have the force, we can put that into Newton's second law and give ourselves an acceleration. And with an acceleration and a small time step, we can find out how much the velocity has changed. And so we can update our velocity. And from our velocity with the same small time step, we can generate a new position. Now we keep looping through that same process by calculating force, getting acceleration, then updating velocity and position, and we repeat that until we're happy with our simulation and we got the information that we need out of it. So that's the basis behind numerical methods.